You are welcome to Master Lucas Academy. The course we have to discuss about today is Organic Synthesis, CHM 416. And we are taking it from Module 1, Unit 1, which has to do with oxidation reaction. So, what is oxidation reaction? First of all, trace it back to what we call redox reaction. So, under redox reaction, it has to do with reduction and oxidation taking place simultaneously. And there are about 4 definitions of redox reaction. But this course focuses more on redox reaction, how it affects organic related compound in terms of what we call organic synthesis. Okay, so with respect to that, we have definition of what we call oxidation reaction in what we call inorganic compound. But it should be noted that the course focuses more on what we call organic related compound. So when it comes to ionic definition of redox reaction, that is oxidation reaction, that is what we call loss of electron, that is net loss of electron. Now, but when it comes to what we call the organic, take note of that. Organic. So organic definition of redox reaction has to do with what we call removal of hydrogen, and addition of what we call oxygen. Take note of that one thing. So in another form, we can also define redox reaction in this place as removal of what we call electropositive elements, and where we have addition of more electronegative elements. Okay, so what are the typical examples of more electronegative elements? Take for example now oxygen. Oxygen is a more electronegative element. So under oxidation reaction in this mentioned organic synthesis, we tend to look at how oxidation reaction affects most of the related compound and how they brought about production of the needed products with the help of the catalyst needed alongside and some certain condition that's involved in production of such compounds. Okay, now from there now we can now discuss more about how this oxidation reaction actually take position in what we call organic molecules. Okay, so the broad form of defining what we call oxidation in organic molecules is oxidation is broadly defined as either the removal of hydrogen or the replacement of hydrogen atom attached to a carbon atom with another more electronegative element, most frequently oxygen. So in a nutshell, that means you are removing the hydrogen from there, you are removing the hydrogen atom from the carbon atom, and you are attaching more electronegative elements, most especially oxygen, to the compound. So now let us proceed based on what we have here. So we're going to be talking about some typical examples in this place. What are the typical examples that we have here? First of all, let's talk about what we call the oxidation, which has to do with dehydrogenation of ethane. So when we're talking about dehydrogenation of ethane, what actually happened here is that ethane originated from what we call the alkane is dehydrogenated. That simply means we remove hydrogen from it. So when we remove hydrogen from it, what eventually happens? It changes to what we call ethene, from ethene to ethane, such as CH3. When we remove hydrogen from it, it came to CH2. Furtherly, when we remove hydrogen from it, it eventually gives us to what we call CH followed by CH. Now, from what we have here on the board, in this place we have removed 2 hydrogen atoms, in this place we have removed another 2 hydrogen atoms, and eventually this is what we have here left. These are another forms of what we call oxidation because hydrogen is removed consecutively from each successful product formed there. This is what we call ethane. This one here we call this ethane, and this one that we have here we call it ethyne. That is the name of the said compound. Now the second one that we also have here has to do with what we call the degree of oxidation decrease, as in the case of the methane. Okay, in the case of the methane, what actually happened there? That is when what we call oxidation of methane. Under the oxidation of methane, what happened in this place? It happens that the methane continue to lose hydrogen to carbon atom to what we call continue to lose hydrogen to carbon atom to what we call carbon to oxygen atom, and so it continues to change from one form to another as the oxidation process continues to take place. Now here we go. Methane changed from what we call methane to another compound form there which is called methanol, and from there, from methanol, it changed to what we call methanol. From methanol, it changed again to what we call methanoic acid. And from methanoic acid, it changed to what we call carbon dioxide. So now, if you look at these stages that we have here, what is the oxidation that is actually taking place here? Now, the oxidation that is taking place in this reaction now is that there is removal of more of the hydrogen atom, and this hydrogen atom are being replaced by what we call oxygen atom, which is more electronegative than the hydrogen itself. Here we go. Let us quickly prove this. Methane is CH4 right from start. Then it's changed to what we call what? Methanol. Methanol is CH3OH. Now, what do you notice there? Oxygen has been added to it. From CH4, one hydrogen atom has been removed for addition of OH atom to make it what? Methanol. When you further the reaction, what will happen? It will change to what we call methanol, where we are going to have C, we are going to have double bond O, we are going to have H here, we have H in this place. This is the methanol that we have there. Then, after the methanol, it changes to what we call methanoic acid. The methanoic acid, here we are going to have what we call C followed by OOH. Put another H here. This is for the methanoic acid. And eventually, it's changed to what we call CO2. Now, what do you notice in this reaction? From CH4 to this, and to this one that we have here, the number of hydrogen continues to decrease, while the number of oxygen continues to increase from methanol to methanoic acid. And eventually, the last stage is CO2. Of course, this is what we call oxidation reaction. Now, another one that we also have in this place is oxidation of carbon in organic compounds. So, when we're talking about oxidation of carbon in organic compound, this is what we mean. Oxidation of carbon in organic compound. So oxidation of carbon in organic compound involves the following. What do we have there? Number one, an increase in the multiple bonds order of the carbon atom. What does that mean? Multiple bonds order of carbon atom, it can change from CH, that is carbon to hydrogen bond. It can change to what we call carbon to oxygen bond. From there, it can change to carbon to more of oxygen coming there. Okay, so this is what refers to as multiple bonds order of the carbon atom. Then number two that we have there is what we call addition of oxygen to a carbon atom. You know, carbon, we all know that carbon can catenate. For that reason, they can combine together with hydrogen, they combine together with other related compounds. So addition of oxygen to a carbon atom is also possible. Replacement of a hydrogen atom with what we call more electronegative elements, most especially oxygen, such as replacing a given carbon to hydrogen atom, then being replaced with what? With oxygen, to eventually give rise to what? Carbon to oxygen atom in a given or specified compound. So all these ones that we have mentioned in this place, they are the oxidation of carbon in organic compound. That is how it takes place. Now, the number three we have to discuss about right now is what we call oxidizing agent. We cannot oxidize a compound without oxidizing agents. Why? It should be noted that for most of these organic related compounds, majority of them require catalysts because their reaction is very slow or much more slower compared to inorganic compounds. So it will be difficult for them, to just initiate such reaction without the need of the starting material. So in this case, they need what we call oxidizing agents. We are going to be talking about few of the oxidizing agents here right now. So what are oxidizing agents? Oxidizing agents are the compounds that are rich in what? In electronegative elements, so which can bring about oxidation in a given chemical process. Okay, now we have some of these as what we call oxidizing agents. We have KMnO4, we have K2Cr2O7. We also have the compound of H2Cr2O7. There are many that we use in organic chemistry. The KMnO4 is referred to as potassium permanganate, while this one is referred to as heptachromate 7, and this is referred to as what? The hydrogen heptachromate as well. So all these ones that we are seeing in this place, they are good oxidizing agents that we use in organic chemistry. We can also call this one a chromic acid. Take note of that, chromic acid. So before we can even carry out what's it called, oxidation on a mentioned organic related compound, we have to first of all be able to prepare the oxidizing agents that we want to use in such compound. So we are going to start like this. For the first one that I have there, under the oxidizing agents, we shall be talking about what we call the chromic acid. The chromic acid, which is the compound that we have here. So for this chromic acid preparation, it is prepared by heating sodium, or we make use of what we call potassium, or what we call Cr2O7 with what we call H2SO4. I think this is quite simple to understand here, that when you use sodium or potassium or what we call C2O7 with H2SO4, that is when you are going to obtain this mentioned compound, which is the chromic acid. So there's a replacement reaction, that takes place there. Let me give you the full equation, where you have Cr2O7 2 minus. So in the presence of what we call H2SO4, then it's going to first of all give us what we call H2Cr2O7. So there will be some molecules of water present in the compound. We remove the molecules of water, H2O, and eventually we are going to have H2Cr2O7. So H2Cr2O4, that is exactly what we are going to have there. So this one that we have in this place right now represents what we call preparation of chromic acid. So when they ask you how to prepare chromic acid, you tell them that by the action of what? Sodium or potassium on what? On what's called H2SO4. But take note that it's coming from what we call the Cr2O7, and eventually you have this equation. You can write this equation to showcase what we call preparation of the said compound. Okay, the second one that I have there is oxidation of primary alkanol to carboxylic acid. Okay, so oxidation of primary alkanol or alcohol, primary alcohol, to what we call carboxylic acid, to the carboxylic acid. Carboxylic acid. So with respect to that, when you oxidize them, what is going to happen? From alcohol, it's changed to what we call the aldehyde. Another name for alkana is aldehyde. And from aldehyde, it changed to what we call the carboxylic acid that we want there. So this process is as a result of what we call oxidation process, and I'd like you to know that carefully. Now, another one that we have to discuss about right now is the second one, which has to do with what's called the pyridinium chlorochromate (PCC). Number 3 there is called the pyridinium chlorochromate, which is PCC. Now, this said compound in this place is also one of the typical agents that we use in what's it called, in the oxidation process. So this mentioned compound here, how do we prepare the said compound in this place? The preparation is that it is the reaction between what's called the pyridine. The reaction between pyridine and what we call chromium trioxide, and the Kong HCl. So when we mix of pyridine and chromium trioxide, then we are going to have chromium reacting together with it. So at the end of the day, we are going to have the process involved with the respect to the compound that we have there. So that is when you react what's called pyridine and what we call chromium trioxide. So with respect to the chromium trioxide that we have there, we make use of what we call conc HCl alongside. So and conc HCl. So in the reaction, we can write the equation for the reaction. This is one of the common past questions that asks you to write equation for preparation of pyridinium chlorochromate (PCC). So the equation now, from the past question, where we have C5H5N, this is the formula for pyridine. Then reacting together with what we call ACl, then reacting with what we call CrO3 to eventually give rise to what we call the C5H5NH. Then we have the compound of this being produced alongside Cr2O3Cl. Now, if you look at this equation carefully, you see that nothing is lost in this equation that we have here. This is the exact compound we're talking about, which is what? The pyridinium chlorochromate. Now, PCC. So, the reaction is quite simple in the sense that the hydrogen reacts together with this one and the chlorine reacts together with this one here, okay, and eventually form the PCC compound mentioned in this place. Now, what are the applications of PCC? They can ask you how do we utilize, or what are the applications? Where are the places we can make use of the PCC? So, as a selective oxidation of alcohol to aldehyde, leading to what we call oxidizing 2-phenylethanol ethanol. So, the 2-phenylethanol may be oxidized to what we call phenylacetylaldehyde without subsequent oxidation to what? Phenylacetic acid. So, in this place, we've said it earlier that most of this reaction, when you try to change what we call the alcohol to you oxidize them, the subsequent production of what we call carboxylic acid at the end of the reaction. So if you don't want to produce carboxylic acid at the end of the reaction, is a selective oxidizing agent that can be used in such reaction. So when you make use of this PCC, okay, so it's going to give you the exact needed compound, so without producing another subsequent carboxylic compound. How do I mean by such expression? Okay, let's say you want to produce what we call phthalate precisely speaking, and you are getting it from the reaction between what we call alcohol, then to give you what we call aldehyde. So what you actually need is conversion of alcohol to aldehyde. But there are cases whereby the aldehyde will proceed to give you what we call carboxylic acid. So you don't need the carboxylic acid, all you just need is the aldehyde. So most reactions proceed in such manner. So by using what we call the pyridinium chlorochromate PCC, it will just give you the needed product directly. That is one of the advantages of using what we call PCC as your good oxidizing agent. Okay, now with respect to that, in this place, if you want to, for example, now 2-phthalate ethanol. 2-phthalate ethanol can easily produce with the help of PCC. 2-phthalate ethanol can easily produce what we call phthalate acetaldehyde. So with respect to that, when it produces the phthalate acetaldehyde, it will not produce another related compound which is called carboxylic acid. That's it. Phthalate acetic acid will not be produced. So that is the major function of what we call PCC in such reaction. Now, with respect to this, PCC is a good oxidizing agent then, unlike many other related compounds, that the reaction furtherly produce what we call carboxylic acid. This particular one does not produce carboxylic acid. Take note of that. It does not produce carboxylic acid. Now, in this case, another what's called oxidizing agent we can discuss about it right now is what we call the KMNO4 and what we call osmium tetraoxide. Exactly. There are also another typical oxidizing agent that can be used in the preparation of many organic related compounds. They have their own preparation and they have what's called their own application as well. So let us find out from here right now. Now, take note of this. It's very, very important. It's very, very important. You have to know a suitable oxidizing agent for a compound that you want to prepare. So here we go. The next one there is C, where we have what's called the KMNO4 and what we call osmium tetraoxide. Osmium tetraoxide, which is OSO4. Now, what are the applications of these two that I mentioned there? So, it's either you are using this or you are using this one that I mentioned in this place. Their application includes the one that I want to mention now. So, they must be in aqueous, take note of that. In aqueous phase, react with what we call alkenes to yield what we call 1,2-diene. Now, they react together with alkenes and eventually they yield what we call 1,2-diene. Now, what does that mean? This given compound in this place, when they react together with alkenes, okay, they produce what we call 1,2-diene. I believe you know where that one is actually coming from. The reagent is used to convert what's called alkane into corresponding diol, which is called the glycol. That is, e.g., we have what we call ethane 1,2 diol. That is exactly the compound we're talking about there. By a stereotypical process called the synhydrosylation. Exactly, synhydrosylation. Synhydrosylation. That is the exact process of such reaction taking place, which you can also call the syn addition of two or groups. Okay, because they involve in the formation of intermediate cyclic inorganic, which is ester, that's decomposed to yield diol, is subsequent. Now, with respect to what we have in this place, this is the process involving converting what we call alkanes to 1,2-diols, okay, such as ethane 1,2-diol, which is also called the glycol. The process is called synhydrosylation. Take note of that one there. So the second one that we also have there is using what we call the osmium tetraoxide. Okay, so in this case, gives excellent use of 1,2-diol. This is when they ask you to explain the process. This is also common in the past question. They ask you to explain the process, that's involved in using what we call osmium tetraoxide or KMnO4 to get these needed products. Yeah, so how do you explain that? Okay, but care have to be taken because this osmium tetraoxide it can lead to what we call blindness. Take note of that. So in the course of usage, so one has to be extraordinarily careful, and at the same time it is expensive. So most cases the chemists don't utilize this if the need is not actually required. So mostly we make use of what we call the KMnO4. So take note of that, the KMnO4. When it comes to the KMnO4, which is potassium permanganate, this one is not expensive and it is more safer. So they can ask you what is the advantages of what we call the KMnO4 over the osmium tetraoxide. So the advantages is that the KMnO4 is less expensive, that is inexpensive, and at the same time it is more safer than the osmium tetraoxide, which is expensive and at the same time is toxic. It can lead to blindness. Okay, so in this place, this one gives us the yield that's needed. Okay, so due to purple aqueous KMnO4, this reaction is often used as what we call quantitative test for the presence of alkane. So it simply means we can use it to test for the presence of alkane in a compound. And actually it has what we call the purple color. Okay, so the test here is that if there is any unknown compound given, as a sample, then if you make use of what we call KMnO4 there, that is dilute KMnO4 plus the sample of the unknown organic compound. So what we observe there, color discharged of a gray-black precipitate of MnO4. Exactly. There is a formation of what we call gray precipitate, gray-black. Take note of that. Gray-black precipitate will be formed there. The short form of precipitate, which is PET, will be formed there. So the resulting compound here is what we call alkane. So that means there is presence of alkane in the compound. For the purple color of KMnO4 to have changed to what we call gray-black. Okay, I proceed. Right now, let's talk about what we call ozone. As you all know, ozone is an allotrope of what? Of oxygen, originating from O2. Ozone is found there in the what? In the troposphere of the Earth. So here we go, preparation. How do we prepare this ozone? Because it can also be used as well. Preparation is an allotrope of what? Of oxygen, as mentioned earlier. highly reactive, obtained by passing stream of O2 over high voltage electric discharge. So when you pass the stream of O2 over what's called high voltage electric discharge. So what we are going to get at the end is what we call O3. That is what we are going to get there. That's the preparation of ozone. So what are the applications of ozones in this place? Application of ozones include the following. Number one, where we have ozonolysis. Now, under ozonolysis is the reaction between O3 and alkane to give unstable intermediate that decompose to an ozonide. So in this case, this is actually talking about the reaction between what we call O3 and what we call the alkane. So when the two of them react together, it eventually decomposes and gives rise to what we call the ozonide. Okay, such as the way we have oxide. So this time around, this one is not forming oxide, but it's forming what we call ozonide. Oxide is for oxygen, which is O2. Then ozonide is for what? Is for ozone, which is O3 in most of the reaction. So ozonide is then reduced directly to acetic acid. The ozonide that we have there further reduced to what we call the acetic acid. Okay, so I believe you know what we call the acetic acid by what we call zinc metal. So we make use of what we call zinc metal here, and eventually it yields what we call aldehyde, or it yields what we call ketones. So further reaction produce what we call aldehyde, or it's used to what we call ketones. That is what you have there. Please, if they ask you to define or to explain what we call ozonolysis is a process whereby ozones react together with what? With alkane to yield what we call ozonide. The further reaction of ozonide, okay, with what we call zinc metal reduces it to what we call acetic acid. So acetic acid eventually produces what we call aldehyde that is needed there. So you can see the shape of the reaction as it is here right now. So another compound we have to discuss about in this place, including what we call the peroxy acid or acids. Peroxy acid or acid. That is the next compound we have to discuss about right now. Now, when we're talking about the peroxy acid or acid, now let me quickly take you back to what we call the peroxide. When we're talking about peroxide, you know the role that the hydrogen actually played there, such as hydrogen peroxide, which is H2O2. Okay, so but in the case of this one that we have, we call them peroxide. Of course, one hydrogen is present in them from the word acid. So one hydrogen is present in them. So because one hydrogen is present in them, we call them acid. Okay. So they have general molecular formula. The general molecular formula for this acid is RCO3H. You see this R here can represent alkyl group such as CH3, can also represent what we call the phenol. Take note of that, such as the compound that we have here right now. Please, you must put this on it to show that that is phenol. Okay, and it can also be what we call the benzoic or any other available related compound which can be used there. So in this case, where do we use this acid? Okay, used for oxidation of many organic compounds, like we use them in oxidation of many organic compounds. Take note of that. So here we go. We have compounds such as what we have here, peracetic acid. Peracetic acid, CH3, CO3H, That's one. We also use them in what we call parabenzoic acid. Parabenzoic acid is also there. So where we have pH followed by CO3H, we call it parabenzoic acid. Okay? Another compound that we also have there, we have what we call trifluoroacetic acid. Trifluoroacetic acid, which is CF3 followed by CO3H. That one is also present there. And the last one that I have among them in this place, the last one that I have among them in this place, which is my number 4, don't mind my arrangement there, is M-chloroparbenzoic acid. Parbenzoic acid. Okay, M-chloroparbenzoic acid with the formula M followed by Cl6H4CO3 followed by H in this case. So all these ones that we have in this place, they are the compound where this mentioned per acid can generally be used. So let's talk about preparation of this mentioned per acid. Preparation of the per acid. How do we prepare them? Preparation of this mentioned per acid. So the preparation of what we call per carboxylic acid right now. Per carboxylic acid. Per carboxylic acid. Or we have what we call per acid. Per acid. Okay, right now are usually prepared by the reaction of carboxylic acid with hydrogen peroxide. Now, reaction between what we call carboxylic acid and what we call hydrogen peroxide. So, example of carboxylic acid in this place, we can make use of what we call acetic acid such as CH3COOH. When it reacts together with what we call the H2O2, then what is the name of the compound from there? It forms what we call the peracetic acid, such as CH3. Then we are going to have C double bond O followed by what we call O, then followed by OH. Now, you can see the compound produced in this place. This is quite different from the regular compound that we normally have. So what is actually happening here is that, oxidation is taking place in this place. More oxygen is being added to the ethanoic acid, which is also called the acetic acid, to produce the compound that we have in this place, which is referred to as peracetic acid. This is the peracetic acid. Take notes. Peracetic acid. So a question can ask you to prepare peracetic acid. So what you just have to do is that you write that peracetic acid can be prepared by the reaction between carboxylic acid and H2O2, which is hydrogen peroxide, and it eventually produces the subsequent what we call peracetic acid, which is CH3CO3H. Take note of that. CH3CO3H. That is the compound formed there. Now, these mentioned compounds, they are merely unstable and generally have to be what? To be prepared freshly before use. So if you want to use this mentioned compound for any reasons, you have to ensure that is those mentioned per carboxylic acid or per acid, you have to prepare them freshly. If you don't prepare them freshly, you might not get what you want as a result of deterioration in the given compound. However, performic acid and peracetic acid, for example, are often prepared in what we call situ and not isolated by action of H2O2 on the COOH. Okay. Now, while I continue to round this up, let's talk about applications. Number 1, oxidation of what we call alkanes, which we have discussed earlier. which gives rise to what we call epoxide when it reacts with peroxide acid. Okay, that's one there. Then number two that we have there is oxidation of ketones. So there we have oxidation of ketones, and eventually it converts ketones to what we call ester or lactones. So these are the two applications of this mentioned compound. So we have covered the unit 1 for today from module 1. On our next class, we shall be discussing about the unit 2.